Good afternoon, one and all. I welcome you all to the third session of day one. I take immense pleasure in welcoming Dr. Kannan Srinathan. Dr. Kannan Srinathan is an assistant professor at IIIT Hyderabad. He's an alumnus of IIT Madras, where he did his PhD in computer science and engineering. His research interests include cryptography, distributed computing, and quantum algorithms. He has published over 100 research papers in reputed international journals and conferences proceedings. He is a recipient of the IBM Outstanding PhD Dissertation Award and Microsoft Young Faculty Fellowship Award. I welcome you. I thank you for accepting our invitation. I welcome you, sir, to the session. Over to you, sir.
Introduced to this field, there was a lingering question as to what are the prerequisites. So what should I learn so that I can do cryptography or research in cryptography and understand them? So the list that was given was perplexing, because it was something like you should know complexity theory, you should know number theory, you should know probability theory, you should know information theory and coding theory, and if possible, you should know some quantum mechanics, and the list was populated this way. It was perplexing because what I understood of information security, or say secure communication, one of the main problems in the field, in the early days at least, what I understood of the problem was, why can't the sender and receiver create their own language? Only the sender and receiver know their language. Other people do not know it. And they can just converse in that language, and that's about it. You got your secure communication done, because that is how, when we were kids, we used to do secure communication. So you create a code language which only the sender and receiver knows, and that's about it. And there was no number theory involved, no probability theory involved, no complexity theory involved, far from no quantum mechanics being involved for sure. So first thing that we need to understand is, why does modern techniques in cryptography actually require a lot of mathematics? The answer lies in the fact that the kind of solutions that we were creating in childhood aren't accepted as solutions for the modern problem, because of something called the Kirchhoff's principle. So Kirchhoff's principle states that the security of the system should not depend on obscurity of the algorithms being used, but should depend on the secrecy of the key. For instance, if you are creating a password scheme, you cannot store the password in the machine, and therefore you store the hash of the password in the machine, the shadow, let us say. Now, should not say that nobody knows what algorithm or what hashing algorithm I'm using to store the password file, and therefore it is secure. I mean, that would be like not following Kirchhoff's principle. And if you are actually not following Kirchhoff's principle, then you don't need too much mathematics, because you could use your own proprietary algorithm. No one knows what you're doing, and you, instead of storing the password directly, you can just store f of x, where what is that f is absolutely obscure. No one knows anything about it, and therefore everything looks okay. But Kirchhoff said it only looks okay, it is not okay. His ideas were simply that of reverse engineering and the like. For instance, even if you do not reveal your f, as long as your password file is storing f of the password, say f of x, say f of x1, f of x2, f of x3, and so on, even if you do not reveal what exists, as soon as I look at many f of xi's for several values of xi's, I should be able to reverse engineer what your f is. And therefore, even if you did not give me, it's as good as I can reverse engineer and find out. His ideas were also suggesting that if Alice and Bob, or say two kids that I was talking about initially, were the only people who want to do secure communication throughout the world, no problem. They need not satisfy Kirchhoff's principle. But then, if I have to talk to router 1, I also have to talk to router 2, I also have to talk to router 3, and all the 40 million routers or so in the internet, if I have to talk to, then I need a separate language for router 1, another language for router 2, and so on and so forth. So I would use all the memory that I have or even more to just store the encodings or those languages. So instead, if you have something called the standard, and internet today works on standards, because you don't want every router in the internet to talk or converse in their own language. If you say HTTP, it actually means that it is a separate language, so to speak, for every router in the internet to converse at the application layer. So everyone understands what that is. So similarly, you have TCP at the transport layer, IP at the network layer. So everyone understands what that is, and therefore people can come in and go out of the internet because it is all based on standards. Similarly, when you want to create a transport layer standard for security, or say HTTPS, then you want an encryption standard. For instance, today's encryption standard is AES, Advanced Encryption Standard. Earlier it was DES, and so on. And what do you mean by a standard? So every router in the internet should use the same encryption algorithm, the standard encryption algorithm, that is, to encrypt their data. Now, if everybody in the internet is using the same algorithm, automatically it means that everyone knows the algorithm. There is no point in saying no one knows the algorithm. So by default, it has become mandatory to satisfy Kirchhoff's principle. And given that you satisfy Kirchhoff's principle, things can get difficult. For instance, recall the password scheme. We can now see that is almost impossible to solve. Why? Because even after knowing the hashing algorithm, you should not be able to guess an input for which the hash of the output is what is stored in the password file. Now, who can stop people from trying out all possible passwords and hashing them and checking whether you're getting the hash or not? So from a situation where it appeared to be very easy, if you satisfy Kirchhoff's principle, namely the hashing algorithm has to be made public, you jump from being sort of easy to logical impossibility. And cryptography is therefore really interesting, because it is a field that has to circumvent logical impossible theorems. You have to give a hashing algorithm such that even if you know the algorithm, given the output of it, you should not be able to find the input which will give that output, and that is logically impossible because you can always do a brute force. So you should still be able to avoid people from cracking or breaking into a system, even though it is logically impossible. You have, of course, you may know that we base it on the fact that even though it is logically impossible to do, we are looking for hashing algorithms which will not get broken in a small amount of time. So stuff like that. So, for instance, not only the password scheme is a logical no-go, and how do you prove that certain things are logical no-goes? I'm using a very colloquial sort of a proof. If I'm able to pose a question for which the answer is both yes and no simultaneously, we want to say it is impossible or a logical no-go. Now, that is what it is in general, but you may have to be more mathematically formal to show that it is simultaneously a contradiction. However, we will stick to a very informal way of understanding why should password schemes be impossible to create. Because to the question of should the machine know the password or not, the answer is both yes and no. The machine should know your password, otherwise at the time of authentication, what does it check? The machine should not know your password, because if it knows your password, then somebody else other than you knows your password. People can read it from there. So machine should know your password, yet not know it. So it's a logical impossibility. Cryptography solves it using collision-resistant hashing. Very good. But we're not worried about solution as such. We are saying because it satisfies or solves impossible problems logically, we are interested in the field. So that is our first step. So first step, we want to convince ourselves that the field is interesting. Indeed, it is interesting because it solves not just the password impossibility. There are other impossibilities too. For instance, should this ballot or your vote be revealed to the aggregator in e-voting? So, for instance, if you do not want to reveal to anybody, then nobody can count and find out who is the winner. So you have to reveal it. But if you reveal it, then there is no secrecy. Your secret ballot is no longer secret. The aggregator knows who you voted it for. and therefore this looks impossible. We of course solve this probably with homomorphic encryption, but notice that it is logically impossible to solve, but yet you solve it, and that is good. So for instance, in e-auctions, should the bid that you make be revealed to the auctioneer or not? So if it is revealed to the auctioneer, then notice that he can compare it, but then it is not a blind auction. People know beforehand what your quote is, and somebody could bribe the auctioneer and know your quote and give a lower quote and win the auction. So that's not a very good simulation of or functioning of e-auctions. So we want blinding to be present, but if blinding is present, then where is the way that the auctioneer knows that the code that you originally submitted is the code that's being revealed finally for the comparison? So that's again a logical impossibility. Today we'll talk about cryptocurrencies, and that's another logical impossibility. Should be allowed to spend your digital cash. You should be able to spend the original, but not the duplicate, even though nobody can distinguish which is the original, which is the duplicate. You can make identical copies, and therefore it gets really tricky. Thus, cryptography is interesting. Not just interesting, now we look at the solutions too. So we saw several logical impossibilities which have to be dealt with. You have no other choice, and therefore it is interesting. Because in real life also, if you are doing things which are logically impossible, you do find that there is a lot of adrenaline flow, and you find a lot of interest in solving impossible stuff. So when man found that it was impossible to fly, when he made this first flying machine, it was very interesting. And when man knew that you cannot leave the earth because of gravitation, and you are stuck here, and when he actually computed the escape velocity and built rockets to go to the moon, it was interesting. So similarly, in the digital world, if you know something is impossible, you say you cannot solve password problem, you cannot solve the voting problem, you cannot solve the auctioning problem, you cannot solve the cryptocurrency problem. When you actually get a logical solution, it is interesting. But sometimes it is just more than interesting, like what cryptography is. It is fascinating because of the way you solve it. There are many ways to solve the password problem. For instance, you could store the password in plain text in the password file, and outside the computer you could keep a board saying that anybody who opens the password file is liable to be in prison for 6 months, or there is 50,000 rupees fine, or stuff like that. You could bring in your local police and laws to have a legal stance such that you can circumvent the impossibility. For instance, you could say, I appeal to your moral consciousness that you should not open the password file. That will be an ethical way of circumventing the logical impossibility. There are many ways of making password files solve the problem, but cryptography does not go the way of using policing. It does not go the way of appealing to your moral consciousness. It actually goes the mathematical way. The science that said it was impossible is the same science that is going to be pit against each other and make things possible. So how does cryptography do that? So you are aware that it could actually publish the key and yet keep the encryption secure. That's the public key cryptography. We'll see some of it today. You could actually have authentication. That's the answer to the question, who are you? And yet not be revealing answer to who are you. It could be anonymous too. So there are blind signature schemes. So how does it do all this? So we want to differentiate between information and useful information. So you have the information about the key, but you don't have it in the useful form. So we'll look at examples of this as we go along in a technical way. So to begin with, we want to convince ourselves that the field is fascinating, and therefore we are saying that sometimes you want blinding, yet you want binding, like in e-auctions. So there is bit commitment protocols, or you want compression and still not have collisions. Collisions are when you have in the password scheme, for instance, two passwords hashing to the same value is a collision, two different passwords. So we want to have compression yet not have collisions, and you automatically want to have one-wayness, and that's your hash functions. So there are many pleasing solutions for impossible problems. So far what we have seen is that cryptography is interesting because it solves impossible problems. It is fascinating because it solves them in a very logical and scientific way. We have to look at those ways, so we'll do that shortly. And given that you can solve impossible problems in your own area, like your password schemes and the like, none can stop the growth of cryptography in solving the impossibilities of other areas, and therefore cryptography becomes fundamental. So examples of this include, for instance, there is a field called coding theory, and we want to see that before cryptography, the field was able to solve some problems and was able to prove some other things as impossible, but cryptography circumvented those impossibilities. For instance, there is something called the singleton bound. It says that you cannot detect, you cannot build detection codes beyond a certain level of noise. For instance, how do you build error detection codes? Instead of sending a 0, if you send, say, a 00, and instead of sending a 1, you send 11, and then say 01 and 10 are not valid code words, then notice that if I receive a 00, I got a 00. If I receive a 11, I got a 1, right? But if I receive a 10 or a 11, I'm sure that there is some noise in the system, so I've detected the noise. So 1 bit of toggle can be detected by a coding scheme which will encode 0 as 00, encode 1 as 11, and leave the other two 0, 1, and 10 as non-valid code words. So that is simplistically put, you have a coding scheme, error detection code, which can detect 1 bit of toggle. However, the same scheme cannot detect 2 bits of toggle. For instance, if you send a 00 and it is received as 11, there is no way for the other person to say that you actually sent a 00 which got toggled as 11, or you actually sent a 11. You cannot differentiate between these two worlds. So in general, there is a Hamming distance of the code, and only up to the distance can you detect. And notice that our encoding scheme can detect 1 bit flip, but cannot detect 2 bit flips, because 2 bit flips can convert one valid code word to another valid code word. However, if you want to detect, say, 100% noise, even adversarial noise, adversary can replace one code word with another, then coding theory says that is impossible. No such error detection codes exist. However, in cryptographic world, you need 100% adversarial noise detection. For instance, you write a check to a net bank for say 1,000 rupees, and bank receives 2,000 rupees. Bank should not say 2,000 rupees is also a valid number, so I gave it. So it should be able to detect even 100% adversarial noise, and cryptography solved it using the hash and sign paradigm. And therefore, today, if you look at books on coding theory, it will have impossibility proofs of not being able to build error detection codes beyond a certain level. But then those impossibilities can be circumvented by hashing and signing, and therefore, if you actually want to have error detection codes beyond the singleton bound, you are better off moving to cryptographic solutions, because within coding theory, there are no solutions. Similarly, there is a field called distributed computing, and there are some impossibilities in distributed computing too. So for instance, it says if there are two people who are talking to each other, and one of them is lying, then there is no way for a third person to come and say, pick who is the liar. For instance, if A sends a 0 and B claims to have received 1, you are sure one of them is lying, because it's impossible that both are honest and they can contradict. So A says he sent a 0, B says he received a 1. Now there is no way for C to find out who is correct, who is wrong. And therefore, localizing faults beyond a certain radius is impossible in distributed computing, and that leads to several intriguing results on the possibilities of agreement in systems, and notice that if you use cryptography, you can go well and truly beyond these impossibility results, and that's most of, or in fact all of the talk after this slide is about how to solve Byzantine agreement, and then how to relate it to blockchains, and then use blockchains to solve the cryptocurrency problem. So that's what we will do rest of the talk. So, but there are other basic fields that got revolutionized by cryptography. So simple notion of what is a proof itself. When the proof is randomized and interactive, you can actually prove things in a much shorter length, much more succinct way. You can actually prove it without revealing the proof. These are called zero-knowledge proofs. You can also have proofs which are sort of non-interactive, even though we know that interaction is a must for going beyond the class NP, as we call it. So if you look at mathematics, you have the notion of efficiently verifiable proofs, and a proof under language which doesn't have a efficiently verifiable efficient verifier, so to call, is a problem harder than the class NP. If you want to go beyond the class NP, we want to have interactions. However, there are very interesting ways in which, say, in using CRS model called the common reference string model and other things, where you can convert back interactive proofs to non-interactive and stuff like that. So it's an interesting field there. And then even algorithms got revolutionized, because in algorithms there are something called randomized algorithms, and randomized algorithms require randomness as input. If you give pseudo-randomness as input, by definition of pseudo-randomness, they cannot differentiate whether they are in a world of pseudo-randomness or randomness, and this could be used to actually de-randomize randomized algorithms, and that's a very interesting field in its own right. So basically, where we stand now is that we are dealing with a very interesting field. That's the point one. Why is it interesting? Because we are solving impossible problems. Point two, we are dealing with a very fascinating field. And why is it fascinating? Because we solve it, we circumvent the impossibilities in a very pleasant way. And three, we are dealing with a very fundamental field, because every walk of science that has impossibilities has to deal with them, and one of the pleasant ways of dealing with impossibilities is to bring in cryptography and circumvent it. So let's look at one such example today. The field of distributed computing had an impossibility called Byzantine agreement in certain settings, and had to circumvent it using cryptography, and that led to something very, very interesting. Before that, we need to know the cryptographic primitives. So we'll look at three primitives that are essential for blockchains. So primitive one is your public key cryptography. Primitive two is hashing algorithms. Primitive three is digital signatures, and we'll introduce the mathematics of these three cryptographic primitives, and then try and build our own cryptocurrency, which to begin with we may only partially succeed, and then we'll bring in other field called game theory, and then create blockchains based cryptocurrencies, which will be towards the end of the talk. So if you look at the fundamental problem in public key systems, it is like, how do you publish your key and yet remain secure? So the whole thing depends on the fact that your key can be published in many different representations. The representation that publish the key need not be a very good representation for actually decrypting, whereas it could be very good for encryption. And all this is possible because same information, when represented in different representations, may have different efficiencies for different operations. So let us stick to, say, natural numbers as our information. We want to argue that if natural numbers are represented in one way, then some operations are easy, some operations are difficult. To see examples of that, you can actually look at, say, three popular representations of natural numbers. One is the Roman representation, other is the decimal or say binary, whatever way you want to look at it, and third is the product of primes representation. So you can represent numbers as product of primes uniquely because of the fundamental theorem of arithmetic, which says every number can uniquely be represented as a product of primes. So these are nothing but different ways in which you can represent the same information. However, the way you represent the numbers actually has a telling impact on how much time it takes to perform certain operations. Different operations may take different amounts of time or complexity for different representations. For instance, if your operation is multiplication, then notice that of the three representations we have discussed or mentioned, the product of primes representation is the superior one. Why? Because if I give you two numbers in product of primes form, multiplying them is a piece of cake. For instance, what is 2 power 3 into 2 power 4? You know, it's 2 power 7. However, multiplication in decimal is not as easy. So there are no really linear time algorithms for multiplying two numbers in decimal. There are quadratic algorithms, there are near linear algorithms, but there are no linear time algorithms for multiplying two numbers when represented in decimal. Say, Roman is a hopeless case there, so I will not worry about that at all. Let us compare decimal and product of primes. So multiplication is not so easy in decimal, but is deadly easy if your representation is product of primes. Coming to addition, there are really fast algorithms for addition in decimal or binary. However, there are no known efficient algorithms to add two numbers in product of primes form and give the answer in product of primes form. So addition is very slow in representation of product of primes, but addition is very fast in decimal. And notice that therefore you get a hint of how cryptography can go about solving its problems. It could say encryption is like addition, suppose, and I give you and suppose decryption is like say an operation that is very slow in your public representation. Right? Then we could build schemes which could act as public key systems. More on this in the next slide. So we have or next to next. So to begin with, let us understand that different operations can take different amounts of complexity in different representations of the same information. So same natural numbers, when represented as decimal, will have very fast algorithms for comparison. We'll have very fast algorithms for addition, but we will have medium fast algorithms for multiplication. The same information of natural numbers, when represented as product of primes, will have very fast algorithms for multiplication, medium fast algorithms for comparison, and very slow algorithms for addition. So therefore, it is interesting to find a single way to represent natural numbers which such that you can have addition, comparison, as well as multiplication very fast. So this is a digression. If you are able to do this, it will be very useful because computers will no longer use binary. LKG students will no longer learn decimals. They will learn this new representation in which all operations are very fast. So we know why decimal is popular today, because in the three famous operations in real life, namely comparison, addition, and multiplication, decimal is fast in the two most frequent of them, namely comparison and addition. It is medium fast in the third most frequent, multiplication. You haven't found a better representation, even though they may exist. For instance, there may be some representation which is fast for all the three operations of real life, say addition, comparison, and multiplication. If and when you find such representations, we can be rest assured that all of computers and all of schooling education will have to use the new representation to teach, because The reason why decimal is popular is only because of the fact that it's able to manipulate the frequent operations very, very quickly, algorithmically. However, public key crypto systems is more about slowness. So how do you make slowness to your advantage? If you have the following template, then you can see why you can get your public key systems up and running. The template is, if you are able to create two representations, one is the public representation, say R2, and other is the private representation, say R1, of the same information, the key. So key is the same, say some natural number. So key is the same. It is in two different representations, so public representation R2 and private representation R1. If you have operation, say encryption operation, which can run very fast in the public representation, but its inverse operation runs very slow in the public representation R2, whereas the inverse can run very fast in the private representation R1, then we have the template ready for our public key crypto system, right? Because what it automatically says is that you can publish your key in R2 and nobody can decrypt because it's very slow, but anybody can encrypt because it's very fast. But the authorized receiver who has the key in R1 representation can actually decrypt it fast, right? So we want this template to be instantiated. Even though this template is pretty simple, instantiating this template turned out to be very difficult. In fact, no known instantiation from scratch exists even today, because it is easy to prove that things are fast. So how do you show encryption is fast in public representation? You just implement and time it. How do you show that decryption is fast in say private representation? You give an efficient algorithm. So how do you show that decryption is very slow in the public representation? You just cannot say that my algorithm runs slow. It may be that your algorithm runs slow, but there may be a faster way or another algorithm which can actually crack it very fast. Therefore, people are unable to show, or the mathematics to show that things are indeed very slow, especially the contemporary mathematics fall short, way short, and therefore we are not able to do it from scratch. However, for the first people who conjecturally instantiated this, say the Reivershammer Edelman, saying that if we assume that the representation, public representation is decimal or binary, and the private representation is, say, product of primes of natural numbers, and your encryption is modular exponentiation, say m power e mod the key, e is also public. So if you do this, then computing the modular exponentiation is easy in decimal, but the eth root, whatever that means in number theory, the eth root. So we know what it means. So it means to the power d, where e into d is congruent to 1 modulo Euler quotient of k. People who know the math may relate to it, but need not worry. Whatever it means to take the eth root, so modular eth root, that operation, there is no known algorithm which can do it very fast in decimal representation of the key, whereas in product of primes representation of the key, there are very fast algorithms to actually do eth root also. So this instantiation with the assumption, the famous RSA assumption that eth root modulo n modulo k, where k is given in decimal, there is no known efficient algorithm to do it. With that assumption, we are able to instantiate a public key system. So that is the basics of public key system. Now, similarly, we can build collision-resistant hashing systems. So how will collision-resistant hashing system work as? So we want compression that still ensures that there are no collisions, but that is mathematically impossible because compression leads to collision. So what is compression? Compression is a many-to-one map. So I want to compress a large string to a small string. The domain is much larger than the codomain or the range. Then it is a compressive map, many-to-one map. Collision is two different inputs which will go to the same output. So therefore, a many-to-one map naturally has collisions, and therefore, despite having collisions, and despite knowing that compression implies that there will be a collision, can we have a scheme where it is a compressive map, yet you cannot find the collisions in polynomial time, right? Again, we do not know of a foolproof from scratch way to do this, because how to show that things are slow, the mathematics of today is unable to do that. However, there are ways in which you can amplify the compression, leaving the collision resistance property intact. So for instance, if we have a way in which 50% compression can remain collision resistant, which is far easier than even higher level compression, there is a Merkel-Damgard transform which says we can transform it to any level of compression that you look for. For instance, it says if you have a small h hash function which has a 50% compression ratio, that is, it takes 2n bits of input and gives n bit of output, if it and then remains collision resistant, then it says you can cascade this and build a capital H hash function which has arbitrary compression, that is, it can take any length input and give the same n length output. So it has very high compression, yet will remain collision resistant. So therefore, it simplifies the problem of getting massive compression with collision resistance to getting simple, say 50% compression with collision resistance. So how does it work? It says like you have your H which is collision resistant and 50% compression, take 2n bits of input, give one n bit output Z1, then take another n bits from your input and hash it again, you'll get Z2, then take X3, the third n bits of the input and hash it again, you'll get Z3, then take X4 and keep doing this, at the end you will get n bit of output. You can actually prove that if H is collision resistant, the small h is collision resistant, then capital H is also collision resistant. The proof is not difficult, very intuitive. And to actually ensure that the proof works, they require that after all your inputs are done, you need to append the length of your input as encoded as n bits and pass it along the last leg of H or small h and get an answer. So if you do that, the proof is fairly simple, and you can go through this called the Merkel-Damgard transform. So how do you get the 50% compression and collision resistance? So there are no methods from scratch, but there are methods which work if you assume that discrete log problem is hard. For instance, if you define say H as nothing but say you take two inputs, say x1, x2, and give one output, so that g power x1 into h power x2 into the group operation essentially. So notice that you are taking nearly twice the input length and giving as the output length, so you have 50% compression. Yet, if discrete log problem is hard, we can actually prove that this is collision resistant. Together with Merkel-Damgard transform, you can actually build a provably collision resistant hash function from discrete log problem this way. People have done that. People have also done it without starting from discrete logs. There are algorithms like MD5 which got broken. There are algorithms like SHA-1 or SHA-2 physics and other things that work today. There are many ways, but this is about hash functions. Similarly, there's digital signatures, and you cannot have perfect digital signatures. However, based on public key systems, which we discussed earlier, it is possible to ensure that using your secret key, you can get a signature sigma of your message M, such that using your public key, the verifier can verify it, whereas people who do not know the secret key will find it computationally hard to forge it. So, for instance, RSA signature would actually ask you to do the decryption process using the hash of the message. The decryption process 2 power d. So sign sigma of m, signature of m is hash of m to the power d mod n, where n is the public key and d is your private key. Public also contains e. Therefore, you can verify it whether h of m is same as sigma power e mod n is the verification algorithm. So this is your RSA hash. So in general, if we have public key crypto systems, if we have collision resistant hashing, and if we have digital signatures, which we do have, we are given only the non-mathematical viewpoint or the philosophy of how to get them. But there are many algorithms for public key crypto systems, many algorithms for collision resistant hashing, many algorithms for digital signatures. Main point to remember is none of them is proven from scratch. Everything is provable or heuristic. The reason why they're not proven from scratch is contemporary mathematics is not able to do that. So as simple as that, they're all open. Now, if you have these, the rest of the talk will be to use this as building blocks to build our own cryptocurrency. And by the time we build our own cryptocurrency, we would have understood the workings of blockchain also. Okay, so how do you build cryptocurrency, which I'm calling it, say, my coin, using public key cryptography, collision resistant hashing, and digital signatures? What will happen is that by the time we build, we'll find that it doesn't hold water actually, and you need a field called either you need to get distributed computing or game theory into the picture. First, if you get distributed computing into the picture, you will get some solution, but it may not be very good for open systems, and therefore you bring in game theory, and then you get a blockchain-based solution. So that is what we will learn in the next few minutes. So how do you build my coin? So what do you mean by my coin? So we want to say that if you want to build a cryptocurrency, there are basically two properties that you need to keep in mind, and you will get a currency. You may want to have other features, but two main features are: first feature is that you should be able to publicly generate a coin such that everybody can verify that the coin belongs to you. So that is first aspect. Everybody should know who the current owner is. Second, the current owner, whoever that is, should be able to transfer ownership. So if you have these two properties inbuilt, then you have a currency ready to be in use. And what are the two properties? Everybody should know who the current owner is. That is the property one. Second property, ownership should be transferable. Everybody should see that the current owner has. You should be able to transfer ownership from current ownership to future ownership. So if everybody can verify who the current owner is, and anybody can transfer ownership, the owner can transfer ownership, then we have a cryptocurrency. So we need to have schemes by which we can get these two properties. So let us see how to get these two properties. So first property, namely to verify who the current owner is, or to actually create coins. In fact, very easy. You can just piggyback on the fact that signatures or digital signatures are publicly verifiable. And therefore, everybody can verify my signature. And how do you translate this to everybody can see that I am owner of the coin? Just say I created the coin and sign it saying that I am the owner of the coin. So everybody can publicly verify that I am the owner of the coin, because everybody can publicly verify my signature. So all we are doing is transitively transferring the public verifiable nature of digital signatures to the public verifiable nature of the owner of the coin. How do you transfer ownership? Now, if I take a new sheet of paper and say, I am transferring the ownership to you and sign. So that's everybody can publicly verify. But if you just take a new sheet of paper which is disjoint and independent from this and say, I am transferring the ownership to you, the chances are that things can go bad in the future. Things can be tampered. People can actually add things in between these two. There is no way for you to say that there was no tampering happened afterwards, and there's no transactions in between these two transactions. So in general, what they do is they don't give a disjoint piece of paper and ask you to write. They say you have to store the hash of the previous block into this, so that you can do the following. You can check that the coin that was originally belonging to me now belongs to you, because I have signed that it belongs to you, and therefore everybody can publicly verify it. And if I store the hash of the previous block in this block, then see that no, there can be nothing in between, and you can see that the coin that originally belonged to is the one that now originally belonged to me is the one that belongs to you. There is nothing in the middle, and then it is tampering is not possible, right? So you got a solution which is up and running. It has the property that everybody can see that the coin originally belonged to me and now belongs to you. Now, if you want to do multiple transactions, very easy. So if you want to transfer this coin to somebody else, say Bob, then what you do, you take a fresh sheet of paper and say, transfer this to Bob and you sign it. Now everybody can see that the coin that originally belonged to me is then belonged to you, then it belonged to Bob, and to show that no tampering will happen even in the future, and no insertion of transactions in middle. So you make it a hash chain. So you store the hash of previous block in the next block, then you find that it has the property that everybody can know who the current owner is, and anybody can transfer ownership. So as soon as everybody can know who the current owner is, the current owner will take a new sheet of paper and say, I transfer the ownership to so and such a person, and sign. So everybody can, and then hash of the previous transaction or block is stored there, and everybody, this represents a cryptocurrency because it has the two properties that we are looking for. What are the two properties? One is everybody knows who the current owner is. Other is the current owner can transfer ownership. But it wasn't so simple. So why my coin does not hold water? Let us see. This is one of the main problems. It does not hold water, and to solve this problem, we need a blockchain. So that's how it is. So we will understand blockchains in that way. So what is the problem with this design of my coin? Let's see. So suppose I create a coin, everybody can publicly verify that the coin belongs to me. No problem. I can transfer ownership to you. No problem again. You can transfer ownership to Alice. Absolutely no problem so far. However, nothing stops you from transferring the ownership to Bob. Why? Because we said to transfer ownership. All you need to do is take a new piece of paper, write the new owner's name, and the old owner will sign it. So you said I transfer ownership to Alice. You also said I transfer ownership to Bob. Now notice that there is no way to find out who the current owner is, because current owner is could be Alice, could be Bob, and actually not defined. Therefore, the only reason my coin does not hold water is, as long as it is a chain, it is a cryptocurrency. Why? Because you know who the current owner of the coin is. The moment it is not a chain, for instance, this is called the double spending problem. The moment it is not a chain, it does not have the property of a cryptocurrency, because you don't know who the current owner is, not defined. Therefore, all that needs to be done to actually solve the double spending problem is you should somehow get back the chain property. So it should, as long as it is a chain, you find that you know who the current owner is. Current owner can transfer the ownership, no problem. But if it is not a chain, then it does not have the property of guessing or knowing who the current owner is. So how do you solve this problem? So you should get back to the chain from the DAG or a tree, whatever. So whenever there is a forking, you should say which of them is correct and which is to be orphaned or ignored. So then you will get back the chain. Once you get back the chain, then it's a currency. So how do you know which path is the actual chain and which are all to be ignored? So if you trust a centralized authority like the government or my coin, so if you trust me, for instance, then you can come back to me and ask, which one do you choose? So whichever one you choose, will be the actual chain, and the other ones will not be considered. So if you trust somebody, then you can actually solve it, no problem. However, if you trust somebody like the RBI, yeah, you may actually not even have a chain at all. You can just have a serial number like what you do in our digital fiat currency, and then solve the problem, because you are actually trusting the entity. So you can actually trust the entity to say who the owner is also, right? So instead, we want to have no trust, or we want to have a decentralized system. And therefore, we say that why can't the network agree on what the chain is? So that will be our next solution. So we'll give a simulated trust coin, where we say that we actually solve the problem by making the network agree on which chain to use and which to not. So that will be our way. However, agreement itself will turn out to be very difficult. And if you bring game theory to agree, then you will get what is called blockchains. So we'll talk about it towards the end. So we'll see that if you can trust me, you can simply solve the problem by just publishing the transaction history in my website, and whenever there is double spending, I will choose one of the chains and hash that part, and everybody knows, everybody trusts me, and therefore you can solve it, right? So the problem is that nobody trusts me, and therefore you want to have a decentralized solution. So how do you have a decentralized solution? Just say all the peers agree on the correct chain. So whichever chain they want to agree on, they're free to agree. There's no sanctity about which chain, but it should be made a chain. So you cannot have it split, because then the current owner will not be known. So we just want to maintain a chain. So whichever one of these chains will be agreed upon by all the people. So how do you make people agree upon something? So you run a percentage agreement protocol in the system, and they'll agree on the correct chain. Once they agree on the correct chain, that has the chain property, so it'll have the cryptocurrency property. Job well done. So whenever there is double spending, you run agreement and you agree on which chain, and that will be the solution. Now this solution would be very beautiful, provided your agreement algorithm can do the job of agreement. However, we'll see that agreement per se is not straightforward, in some cases impossible, and in open systems deadly difficult. And that's where we'll bring in a third field called game theory and solve the problem, and the end solution will be named as a blockchain solution. So let's see what is the agreement problem and why is it so difficult. So it is a fundamental problem in cloud computing. So it says that you have a set of processors or players, and their goal is to agree on the same answer, and the answer should be the input of some honest player. So look at it this way: you want to agree on just say 1 bit for now. If you can agree on 1 bit, you can agree on many. So each processor player has 1 bit of input, and you want to run a protocol at the end of which every non-faulty process outputs the same value, and that's called the agreement property, and that value should be equal to the input of at least one non-faulty process. So this is the technical version of the problem. Now, intuitive way of viewing this problem would be how do you simulate broadcast in a peer-to-peer system? If you can simulate broadcast in a peer-to-peer system, you can solve percentage agreement problem also. For instance, we can let each of the peers to broadcast his input, and everybody knows everybody's input now, and then you can apply some local function on the entire broadcasted data to actually make everybody agree on the answer. So if you have a broadcast, then you can solve percentage agreement. The vice versa also is true. If you have a percentage agreement protocol, you can solve broadcast as follows. So first, you unicast your data to everybody, and then they run an agreement protocol and they agree on the answer. So it's as simple as that. However, even broadcast in peer-to-peer systems, if it were possible, you could have used it, but it's not possible to actually do that. Why? Because the first solution that strikes our mind to broadcast data is, why can't you send the data to everybody? Why can't a collection of unicast simulate broadcast? The answer is that That's not good enough. Let's see why. Suppose you have a network. So sender A wants to broadcast it to, say, network has only two more people, let us say, B and C. So sender A wants to broadcast some information to B and C. There is no broadcast channel. It's a peer-to-peer system. If you have a solution like, okay, why don't you send your message to B and then also send your message to C? So why can't that be a way to broadcast? If you do that, notice that there are settings or scenarios where after sending your message to B and before sending your message to C, you may fail. There may be a power failure. Then notice that we wanted to do atomic broadcast, but atomicity property fails here because as far as B is concerned, broadcast happened. And as far as C is concerned, broadcast this did not happen because it never got any message because you failed before sending it to it. So simply saying a collection of unicast will simulate as though a physical broadcast channel existed is tricky. You cannot do that. And when you have Byzantine faults, Byzantine means you can actually have active control over the code you are running. Then things get even more tricky because a Byzantine sender could send a message M1 to A to first player, say A sends M1 to B and A sends M2 to C, and therefore A is confusing the network by sending M1 to B and M2 to C. If there is a physical broadcast channel, this is never going to happen. Either he has to broadcast the same value or not broadcast at all. However, simulating broadcast in peer-to-peer system in a Byzantine environment gets even more tricky. Just not the atomicity property alone. It has the property of agreement also going to the extent that people can confuse what to agree on because you can send different messages to different parts and in your cryptocurrency problem, it is accentuated. Why? Because a person who did double spending could broadcast the first kind of spend to the left side of the network and second kind of spend to the right side of the network, and the two parts of the network, as long as they're getting different data, are never going to agree. And how do you actually make them agree? So agreement is that tough. In fact, agreement is proved to be impossible in a network of 3 nodes where one of them could be Byzantine. So we look at the impossibility proof not because we need it for understanding blockchains, because it is interesting in its own right, and it could be of some learning merit in a world of distributed algorithms. However, notice that we will also look at it because we can see that if digital signatures can exist, then this impossibility can be circumvented. And therefore, we can view this as a proof of the impossibility of perfect signatures also. So that's another way to view this. So let's see the impossibility proof. So suppose a Byzantine agreement protocol exists in a network of 3 nodes. We'll get a contradiction. And what is the contradiction we'll get? We'll show that there must exist a network which has, if Byzantine agreement protocol exists, there must exist a consistent network alpha on the right side on the screen. However, we'll show that alpha is inconsistent and therefore the protocol cannot be solving Byzantine agreement. So let's see how do you prove. So suppose there is a Byzantine agreement protocol in the triangle ABC. What does it mean? If you say A is faulty and B and C are with input 0, the agreement condition says B and C should output 0, and therefore we know that B and C in the network alpha 1 in the triangle will output 0. However, if we can ensure that, or if the adversary behaves as a split personality, because A is faulty, so A can do whatever he wants. So what is the particular strategy we want A to follow? If A acts as split personality, that is, A behaves like A with input 0. Basically, A behaves like the A in alpha and with B, and A behaves like A dash in alpha with C. That is, whenever talking to B, he will talk like his input is 0 as he does in network alpha. And whenever he talks to C, he will behave as though his input is 1. He'll behave like A dash. And at this point, notice that the nodes B and C cannot differentiate whether they are in network alpha 1 or they are in network alpha. Why? Because at any stage, B is talking to C and talking to A, the same thing in alpha as well as alpha 1. And similarly, C is talking to B with input 0 and talking to A with input 1. And therefore, B and C together cannot differentiate whether they are in the network alpha or they are in network alpha 1 where A behaves like a split personality. A splits himself as A and A dash. So because A splits himself as A and A dash, B and C cannot differentiate alpha 1 and alpha. However, in alpha 1, B and C decided to output 0 and therefore in alpha also they have to output 0. Similarly, we can argue that if C behaves like a split personality, then A dash and B dash with input 1 cannot differentiate whether they're in alpha 2 or alpha. And in alpha 2, they have to agree on 1 because you said you're running a Byzantine agreement protocol there. Therefore, A dash and B dash have to output 1 in alpha. The contradiction comes when you see that when B behaves like a split personality, A dash and C also cannot differentiate whether they're in alpha 3 or alpha. But in alpha 3, they say you said they will have to agree because it's running a Byzantine agreement protocol. But C already decided to output 0. A dash already decided to output 1. So agreement is impossible. Right? So this is what is the impossibility proof for agreement even in a synchronous network. However, there are ways in which you can make this possible if digital signatures exist. For instance, this whole thing works with the intuition that I mentioned earlier, that if A sends a 0 and B receives a 1, or claims that way, there is no way for C to find out who is faulty. And that is what they are using in the impossibility proof to the in a formal way. However, if digital signatures exist, we can give protocols. Why? Because even if A sends a 0 and B claims to receive a 1, C can find out who is the liar if digital signatures exist. And how does C do that? C will just inquire with the receiver, say B, you are claiming to receive a 1, show me A signature on 1. Now, if B is a liar, he cannot show A signature on 1 because he actually received a 0 from A. However, if he produces A signature on 1, C knows A is the liar because there is no way for B to get A signature on 1 unless he sent 1. Therefore, if digital signatures exist, you can actually localize the fault. If you can localize the fault, you can remove that guy and the rest of the protocol is straightforward. Therefore, fault localization is possible if digital signatures exist, but we know that fault localization is impossible otherwise because we showed that Byzantine agreement is impossible in general, and therefore reading these two together, what it means is perfect digital signatures are impossible. However, we know we are not looking at perfect world. We are happy with digital signatures which have a small probability of error and which assume that the adversary is computationally bounded, and those are the signatures we have today. But they are practically acceptable because in practice it's indeed true that small probability of error is okay, and it's also indeed true that nobody has infinite computational power or super polynomial computational power, and therefore together with this we can build authenticated Byzantine agreement protocols or practically secure Byzantine agreement protocols, and therefore this is one of them for 1 out of 3, but you can extend it for the entire network, and therefore we know how to build cryptocurrency this way. And how will it be? It will be simply the following. You make the network agree on the correct chain. And how do you make them agree? Run a Byzantine agreement protocol so that everybody agrees on which is the correct chain. But this also has a very big problem. To actually run a Byzantine agreement protocol, you need to know who are all the people who should agree. But in strictly open systems, where anybody can come in at any time, anybody can go out at any time, nobody knows at any given instant who are all the people who have to agree. In fact, nobody keeps track of who are all the people who are there. So in open systems, solutions will not work. Whereas in closed systems, where you know who are all the people who have to agree, we can run agreement protocol and make them agree. If you want everybody in the system to agree, you should know who are all everybody in the system. But in an open system, nobody knows who are all there in the system anyway, and therefore you cannot make them agree. And in fact, if you look at the protocol, the protocol may run in collection of rounds, and therefore it takes some amount of time to make people agree. And within that time, there could be a lot of churn in open systems. So what you started off trying to make 100 people agree, and by the time you made them agree, they left and another 100 people came in, and that will be a big joke. So therefore, in closed systems, we can have solutions without game theory, but in open systems, we have to bring in game theory and solve the problem. And that is the solution, which will be called as blockchain. And the solution is this. At this point, it may not take a lot of time to understand the blockchain approach, because we know all that the blockchain has to do is come up with a method in an open system such that everybody can agree on which chain to harp on and which chain to harp on. So if you bring in game theory and if you incentivize honesty, you see that you can solve it. So I'll give you the approach in one slide, and then we can understand and discuss why and how it is instantiated in Bitcoins and how it is instantiated in other places. So suppose you publish the transaction history, and at this point, suppose we assume that it's not only me who will add the block, but anyone can add the block. And it's not just anyone who can add the block, that person should not have any control. The person who adds the next block should be randomly picked. Now, why this is important will be clear by the end of the slide itself. But suppose for now, apart from publishing the transaction history, you don't hand over the control of adding a new block to one guy. You say anybody can add the block, usually called the miners. Anybody can add the block, but nobody should have any monopoly. That is, nobody should have any control of saying that I know when my chance will come. Nobody knows when their chance will come. They'll be randomly picked. How to do that, we'll see. That's a special instantiation that we'll do see it in next slide. But suppose by chance you are able to randomly pick who should add the block, suppose. Then notice that at this point, our state is the following. All the double spends are detected because everything is there for everybody to see that double spending happened, but there is no centralized authority to correct it. Correct it in the sense, find out which chain it is. And at this point, what did we say? We say that, okay, let all the peers agree on what the correct chain is. Now, how did we agree? Either you run a bicentennial agreement protocol if it's a permission system or a closed system, or if it is an open system, we do not know how to agree. Blockchain approach is to answer this particular question, how to make people agree even when you do not have a closed system and do not know who all should agree. So even when you do not know who are there to agree, you can make all the peers agree as follows. So look at the idea. The idea is simply three sentences. Sentence 1. The longest chain is deemed to be the one that you agree on. Sentence 2. Appending in the longest chain is rewarded. Sentence 3. Appending elsewhere is penalized. Sentence 0 is there's no monopoly. People who want to add will be randomly picked. Now, if I read these 4 sentences together, it will be clear why it works. Let's see why. You are randomly picked, and therefore the person who gets picked to add the next block will get a chance once in a blue moon. If he adds to the longest chain, he will get a reward. If he adds elsewhere, he will be penalized. And the longest chain is deemed to be correct. Notice that if I get a chance once in a blue moon and I have to add, I will only be adding in the longest chain and making it even longer. Because if I add elsewhere, I will lose money. I will be penalized. If I add in the longest chain, I will be rewarded. And I don't know when I'll get my chance. So if at least I am not randomly picked, but I am the only one around, then I can actually make a shorter chain long enough after some time. So there's at least some chance. But if I know that I have no monopoly and I will be randomly picked, then game theory suggests that if the longest chain is formed, then that chain will uniquely remain so in the equilibrium also. There will be only one unique longest chain in the equilibrium, and you can deem that to be the correct chain. So eventually there will be only one longest chain because game theoretic equilibrium will end there. How do you know that? We know that because you are randomly picking, and therefore rationally anybody knows I'll get a chance once in a blue moon. There is no point losing money by adding elsewhere. Where it's only rational to actually add in the longest chain and collect my reward. So therefore, if you are able to implement a way to randomly pick who should add the next block, and if you are also able to give reward for adding in the longest chain, and if you are also able to penalize for adding somewhere else, and then you can deem the longest chain to be correct one, and you have solved the agreement problem of which chain to agree on. And since you agree on the chain and remove everything, it gets back the property of a currency because you know who is the current owner, and he can transfer ownership. So that's the story. So only thing that is left for us to understand now is how do you get these four things done. One of them is easy, that is longest chain is deemed to be correct, straightforward, we leave that. How do you get the other three done? How do you pick people randomly to add? How do you actually reward for adding in the longest chain? And how do you actually penalize for adding elsewhere? So these are the three things that we need to learn. Now, you could run three different protocols. You could say run a protocol to randomly pick the next person to add, run some protocol to reward if he's looking at where he's adding and then reward him, and you could penalize if he's adding elsewhere. So you could do all that. But Bitcoins, for instance, created a very, very pleasant way of getting all these three done in one go, in single shot, using the concept of proof of work. It said, I will do random selection. I will also give incentives and also penalize by simply using the concept of proof of work. And therefore, it became very pleasant. Now, what is proof of work? So only if you give some proof that you worked very hard, will you be allowed to add, right? That's the first statement, right? So if you should prove that you worked very hard, only then you should add. Now notice that what does this mean? This means there is penalty for everybody because you have to pay an energy bill. You are giving a proof that you spent a lot of money or energy in doing the work, and therefore you are putting your energy bill, and therefore everybody is automatically penalized. Wherever you add, you are penalized because you are only allowed to add after you give proof of work. Therefore, penalty is universal. Now, giving reward is easy because penalty is universal. If you ensure that you give more than the penalty, you give reward for the longest chain, it's fine. Now, cryptocurrency is a currency by itself. So giving the reward is fairly straightforward. From thin air, you can add a new transaction saying, put into my account some number of Bitcoins. So initially it was 50 Bitcoins, then 4 years later it became 25, then 4 years later it's 12.5 now. So reward system is straightforward. From thin air, you can mint money and put it in your account. So at this point, you see that adding in the longest chain will be rewarded. Adding elsewhere will automatically be penalized because penalty is for everybody. But reward is more than the penalty for those people who add in the longest chain. So net to net, there is reward. So why is reward more? It is more only if the value of Bitcoins is that high. So if Bitcoins is value 0, then any amount of Bitcoins is not going to match the penalty, that is the real electricity bill that you have to pay. So if as the Bitcoin value increases, the reward increases, right? So there is reward to add to the longest chain. There is penalty if you add elsewhere. How do you get the random selection using the same kind of, in the same system? Now, what kind of proof of work? So if you give proof of any work is not enough because we want random selection also. So we say the proof is as follows. We said the hash of the previous block should be stored in the next block. Now, if you say that the previous block can have another attribute or field called the nonce means some random number, and you put a rule that the hash of the previous block should be less than some threshold, right? That's the hash puzzle, what we call. The hash puzzle is hash of the previous block cannot be anything, but it should be less than some threshold. Then notice that there is no guarantee that hash will be less than the threshold. So you have to keep changing the nonce and trying it out again and again. So till you actually hit upon a nonce where the hash will be less than the threshold. automatically that becomes a proof of work, because you have to keep trying. And therefore, if you hit upon a nonce where the hash value is less than a threshold, you have put in a lot of work. That's there. So proof of work is there already. And how is random selection coming in because of that? Notice that nobody knows who will be the winner, because everybody keeps trying in their own way, and the first person who wins will actually add to the chain, and from then on the chain would have grown, and the next person, the definition of previous block would have changed because of that, and therefore now people have to restart and try again. And therefore the first person who hits upon the nonce such that the hash of the block becomes less than the threshold will be the person who will be adding. And there is penalty for adding elsewhere, because he has to pay an electricity bill. There is a reward for adding in the longest chain, because that is the uh, uh, Bitcoin's incentive. You are able to incentivize people to add in the longest chain. And third, there is random selection, because nobody knows beforehand whether they are going to be the first person who win or not. And together we see that you have solved the problem, right? So to summarize, so if you do only cryptography, you will get my coin, but it will not solve the double spending problem. If you do cryptography and distributed computing, you can solve the double spending problem by making people agree on which chain is the correct chain, and that agreement is possible by running a bicentennial agreement protocol in a closed system. But in a completely open system, you need a blockchain solution. It says that not only crypto and distributed computing, you bring in game theory also and say that you have the property that there is randomness, there is longest chain is assumed to be correct, and there is reward for adding the longest chain, and penalty for adding elsewhere, and there is randomness that nobody has monopoly. Then you will get a blockchain solution, right? So before I conclude, I'll just say that we are in the tip of the iceberg. The future of this area is tremendous and unimaginably brilliant. And why we say that? So notice that we did banking without a banker. How did you do banking without a banker? So you decentralize the banker. How did you decentralize the banker? Using the blockchain approach. And what does that mean? All that you did is you said there is the longest chain, and the longest chain will be game theoretically in unique equilibrium. Why? Because there is penalty for adding elsewhere, and randomly chosen guy, and the person is rewarded if he adds to the longest chain. So you got a cryptocurrency, and you are able to decentralize the banker. In future, there is not only that you can decentralize the banker, you can try and decentralize almost everything. And with what guarantee will we say we can decentralize almost everything? We will say it with the following guarantee. We know that cryptocurrency decentralizes blockchain. We will now show that decentralization of something much more tougher has already happened, and then everything else in between these two, and therefore sandwich property says that everything in middle also should have a solution. So what are the things in the middle? So you can take decisions without a decider. So for instance, you can have a decentralized governance. You can write stories without a creative writer. You can decentralize creative writing. You can make discoveries without a scientist. With what guarantee are we saying that all these are going to be possible? The guarantee is we'll show that there is something that has been decentralized already, which is much tougher than this, and there is something that is decentralized already that is easier than this. That is, cryptocurrency is banking without a banker is easier than this. That has already been done. We'll now show that the other end is also done, and therefore in between all this also have to be done eventually. So you can prove theorems without a prover. You can invent gadgets without inventor. You can do anything without the doer. And to give you the guts or the guarantee, we'll now show that the other end is already been done. What is the other end we are talking about? So we can evolve creatures without a creator. So how do you know that you can evolve creatures without a creator? How do you decentralize creativity itself or creation itself? Simple. How did we do evolution of creatures without a creator? Blockchain approach. And what is the blockchain approach? When randomness meets reward, meets penalty, meets longest chain, you can do things without the doer. And what did nature do to evolve creatures without a creator? If you know the Darwin's theory of evolution, It is nothing but randomness meets longest chain meets reward meets penalty. That's all it is. So what do you mean by survival of fittest? That DNA that survived the longest is the fittest. So a fit means you live long, right? Your DNA should survive long. So the longest chain of DNA is the fittest chain. So therefore, you're saying survival of fittest is nothing but the longest chain. Now, what is the penalty for being outside the fittest chain? Death is a penalty. There are predators, prey. So basically, if you are not the fittest, you cannot survive. So you create a situation where there is penalty for not being the fit. So if you are not in the longest chain, there is penalty. You will die, right? So there is penalty for not being in the longest. You will die. What is the incentive for being in the longest chain? The incentive is the pleasures and the automatic hormones which incentivize you to actually increase your progeny. So there is, you find that the chemistry is so created that there is a lot of incentive to actually grow or to actually grow your progeny. Say every gene wants to propagate, right? So you have a chemical incentives for growing the longest chain or growing every chain. In fact, there are death penalties for not being in the longest chain. And of course, if randomness is not involved, nothing happens because you will have monopoly. Even a dead DNA can monopolize and do. Therefore, what we want here is randomness. So you have to have random mutations so that there is no monopoly of a DNA. Truly, only good DNAs will be there because no DNA is having any monopoly over the system. So when you have no monopoly over the system and the longest chain meets non-monopoly because of randomness meets penalty for not being in the longest chain meets reward for being in the longest chain, we find that you can do things without a doer. Nature has already been doing evolving creatures without a creator. That is a very, very tough problem, but it has done that. We are doing banking without a banker, and therefore there is no surprise that anything in between eventually will also be decentralized. So with that, I'll open for questions.
Thank you, sir. There's one question by Ms. Swaroop Rani. That since there is a need to store hash of previous blocks, does not it create overhead when the network is expanded? Is it scalable?
Good question. So there is a need. So not is it scalable? So if you look at it, if you have to always remember the entire history, then the scalability problem crops up. But if you know a concept called say Merkle trees, then notice that hash of a hash can also be used for similar verification purposes, and therefore you need not remember the entire history. You can actually remember the hash of the entire history is as good as really remembering the entire history with respect to this particular tamper proofness of the problem, right? And therefore, to make it scalable, people do not store hash of the data or the block directly. What is stored is the Merkle tree's root. Merkle tree is nothing but you have all the data in the leaf. Then two hashes of the leaves are then hashed again, and then those two hashes are hashed again, and hash of hash. You build a hash tree, and finally you will get a root hash. And therefore, irrespective of how many leaves are there, the final root will be fixed length, and that is the one that is sufficient to be stored. So what we did now is the philosophy of blockchains and the fundamental principles to make it scalable. Practical solutions actually use Merkle trees. They don't store the hash. They store the Merkle root to make it scalable.
So we have one more question from Dr. Sumalata Aradhya. Sir, for IoT, there is a community, IoTA, and it provides a solution for blockchain. but it makes use of coordinator. How to achieve decentralization here?
So you want to decentralize the coordination, right? That's the question.
Yes, sir. Yes, sir. It is there in the chat box.
How do you use the chat box? Just looking.
She's asking, for IoT, there is a community IoTA, and it provides a solution for blockchain, but it makes use of coordinator. So how to achieve decentralization here?
Yes, question is valid and answer is yes, it is possible to decentralize. It's like, how do you do that? So notice that if you, so far what we have done is stored data on top of the blockchain, like in Bitcoins, the transaction data. But notice that it is also possible to store entire programs, because programs are also data, and execute programs on top of blockchains, and those are called smart contracts. So they need not be a contract. They could be any program, actually. I don't know why they are restricting to call it smart contracts. So notice that you can decentralize computation and not just storage of data. So if you decentralize storage of transaction data, you will get a cryptocurrency. However, because programs are also data, instead of asking miners to only verify the data, they can actually execute the code and verify. Therefore, you could actually decentralize code itself, computation itself. How do you do that? By smart contracts. So if you then notice that your particular decentralization requirement, namely of the coordinator, is a program. So if you have a centralized way to write a program to coordinate, that particular program can be instantiated as a smart contract on the blockchain, and that will become decentralized version of coordination. So to be precise, I'll repeat again. So if you store data on the blockchain, that is tamper-proof data. If you store programs on the blockchain, you can execute programs on the blockchain in a tamper-proof way, and in technical research, those are called smart contracts. Now, smart contracts need not be contracts; they can be any code, and therefore, how do you decentralize your particular coordination? You take the code that is coordinating and put that code as a smart contract on blockchain. You will automatically decentralize.
Okay, there is one more question from Ms. Purnima Girish Nayak. What is the role of nonce in block?
Yeah, so I'm able to see the chat now. Yes. Role of nonce in block. So if there is no nonce in the block, then we said the hash puzzle is that the hash of the block should be less than a threshold. So there should be some way in which the hash of the block can be made less than the threshold. Now, if the block is fixed, then if you hash it and it doesn't get less than the threshold, you are stuck. Therefore, what we do is have a nonce in the block such that you can keep changing the nonce and changing the hash. For some nonce, certainly the hash should be less than the threshold is the field, because the total number of nonce will be much greater than the total gap in the threshold. Therefore, we quickly see that for many nonce, but not all, the hash value will start with 30 zeros. That is, it will be less than some threshold. Therefore, you can give proof of work as follows. You say, give me that nonce whose hash along with the transactions, the entire block's hash is less than the threshold. So the role of nonce is to have this hold of changing the hash of the block. If you don't have the nonce, you have to change the transactions, which is getting very tricky. Therefore, even for fixed set of transactions, the nonce helps you to change the hash of the block and meet the puzzle of hash should be less than threshold. That's the role.
We have one more question from Navneet Singh. How to increase scalability without compromising the performance of blockchain?
So notice that if there are too many miners, right? So we are worried about a problem, namely, which is environmental, right? So increasing the performance of the blockchain and the scalability of the blockchain are trade-offs, true. But the most important thing that we are worried about today is not about scalability or performance. If you have too much of mining, then there is lot of energy that is wasted. If you are wasting that much amount of energy, then you will be adding to the global warming. So the most important problem is that you can actually create or accentuate global warming and accelerate it if you actually waste so much amount of energy. If that is not in our mind, if we just need to see a scalability without compromising the performance, notice that the fact that we went to blockchain itself is to make it really scalable in an open system. Otherwise, you have to keep track of who are all there in the system and so on. So open systems are naturally scalable, and you find that the performance of blockchain is not affected because as more and more miners join, more and more trust is developed and more and more value is there. And as more and more value is there, more and more reward is there. As more and more reward is there, more and more miners will be interested. As more and more miners are interested, more and more trust will be developed in the system. Again, as more and more trust is developed in the system, the value will increase further. So basically what we are saying is trust begets value, value begets size, and size can beget trust. And therefore, this cycle will keep on running. So no issue there. But the issue is environmental issue is there.
Yes, so there are no more questions. I think there are no more questions.
What was the scheduled time for 4 o'clock?
Yes, sir. I think we can wind up now.
Okay.
Sir, I thank Dr. Kannan Srinathan for an excellent presentation, providing an in-depth knowledge on the cryptographic primitives of blockchain technology, which proves to be a good source of knowledge acquisition on working of blockchain for beginners. Thank you very much, sir. Sir, you have to unmute yourself.
Yeah, so thank you.
Yes,
so can I disconnect?
Yes, sir. Yes, sir, sure. Thank you very much, sir, for accepting our invitation. Thank you. It was an excellent presentation, sir. Thank you. Thank you all for attending the day 1 session. We'll meet tomorrow for the day 2 session, which is fully on smart contracts, Ethereum smart contracts. Thank you.
Ma'am, I have a point to say.
Sorry?
I have one thing to say. I have sent you a mail regarding the name.
Yes, ma'am.